Namaste, I'm Vrushali. Welcome to my channel. In this video series, we will go through each chapter of data intensive application. Basically, this book is written by Martin Kleckman. Book is divided into three parts. Part 1, which is all about fundamental concepts, which can be help to design data intensive application. Part 2 describes how data can be distributed across multiple machines, and when we distribute data, what variety of unique challenges it brings. Part 3 describes how we can put everything together and design a beautiful, scalable, and reliable system which is efficient and maintainable. So let's start. When we can call application is a data intensive. If data is a primary challenge, the quantity of data, the complexity of data, and the speed at which the data is changing. How can we achieve to design and build data intensive applications? If you have worked in software engineering, especially server side or backend systems, you have probably been bombarded with plenty of buzzwords like NoSQL, big data, web scale, sharding, eventual consistency, ACID, cap theorem, and the list goes on. What are these buzzwords used for? These buzzwords are all related to storage and processing of the data. In this video session, we will try to find useful ways of thinking about data systems and how it can help us to build it. We also learn how data intensive system works, why they work that way, and what suggestions or what questions we need to ask when we build it. So let's begin. What we expect when we talked about server-side backend system. It should be reliable, scalable, and maintainable. When we can say particular system is very much reliable or scalable, let's understand all these concepts into this chapter. So, agenda of the chapter will look like this. What are the bigger problems today we face in software engineering? Many applications today are data intensive vs compute intensive. When I say data intensive or compute intensive, what is the meaning of that? Data intensive applications are generally make an intense usage of data in all its heterogeneous forms, whereas the compute intensive applications are compute bound, where CPU cycles are the bottlenecks. If you see, CPU clock speed are barely increasing. Multi-core processors are standards. Network are getting faster. This means parallelism is only going to increase. So, when we build data intensive application, we make use of few standard building blocks. What are those building blocks? Many applications need to store data so that they or another application can find it again later whenever they require. Different databases are available to solve this challenge. We have to remember the result of an expensive operation to speed up the reads. So we cannot put everything into database and fetch it from there. So we have to build caches in that case to save the cost and the time. Next challenge is allow users to search data by keyword or filter it in various ways. Search indexes is getting used as a main building block. When we say data intensive application parallelism plays important role, what is the exactly meaning of that? We can send message to another process to be handled asynchronously on behalf and return the result of the operations. Stream processing technique is getting used to achieve this. And lastly, We also need to periodically crunch large amount of data into smaller parts, and batch processing work effectively here. Now, if we take a look to these building blocks again and read about database, caches, search index, stream processing, and batch processing, we think that it is very obvious to implement these uh, building blocks. And it's so why it sounds obvious? That's just because data systems are such a successful abstraction. When we use them all the time, that so we can use them all the time without thinking much. When we think about data systems, we typically think about database, queues, and caches. Although DB and message queues have superficial similarity, both store data for some time. They have very different access pattern, which means different performance characteristics and thus very different implementation. Let's take an example of possible architecture of data system that combines several components. When you combine several tools in order to provide service, the service interface or application programming interface API usually hides those implementation details from the clients. So here, if you see the diagram in a detailed way, the user is talking to the application over the API, but underlying application or API calling the application code and using the building standard building blocks. We just saw it in previous slides. When you design data system or service, a lot of tricky questions arise, like how do you ensure that the data remains correct and complete even when things go wrong internally? How do you provide consistently good performance to the client even when part of your systems are degraded? How do you scale to handle increase in load? What does a good API for service look like? There are many factors that influence the design of a data system, including skills and experiment of the people involved in the project, legacy system dependencies, the time scale for delivery, regulatory constraint, organization tolerance for different kind of risk. We focus the three main concerns that are important in most software systems: reliability, scalability, and maintainability. What is reliability? The system should continue to work correctly, even in the face of adversity, means hardware or software faults, or even a human error. What is scalability? As the system grows, there should be reasonable ways to dealing with that growth. Third is maintainability. Over the time, many different people work on the system. Those are developers, quality engineers, and data engineers. All of them will maintain current behavior and adapting the system to use new use cases. They should all be able to work on it productively. So let's deep dive and understand various algorithms are used in order to achieve reliability, scalability, and maintainability. What it means for something to be reliable or unreliable. Everybody has an intuitive idea to this question. For software, typical question expectation include the application performance. The application performs the function that user expected. Software can tolerate user making mistake or using the software in unexpected ways. Software performance is a good enough for the required use case under the expected load and data volume. Software system prevents any unauthorized access, and abuse. If all those things together mean working correctly, then we can understand reliability as a meaning roughly continue to work correctly even when things go wrong. What is the difference between fault and failure? The things can go wrong are called faults, whereas the system that anticipate faults and can cope up with them are called fault tolerant or resilient systems. A fault is usually defined as one component of the system deviating from its peak, whereas failure is when the system as a whole stops providing the required service to the user. It is impossible to reduce probability of fault to zero, and therefore it is usually best to design fault tolerant mechanisms that prevent faults from causing failures. So, prevention is better than cure. Although we generally prefer tolerating faults over preventing faults, there are few cases where prevention is better than cure does not work because there is no cure exist. Where does this apply? This is the case with security matters. For example, if an attacker has compromised the system and gained the access to sensitive data, that event cannot be undone. Let's talk about the fault which can be cured. We will discuss how reliability matters or hampers with hardware faults, software error, and human error. When we think of cause of the system failure, hardware fault quickly come into mind. Anyone who has worked with large data centers can tell you that these things happen all the time when you have lot of the machines. A software bug that causes every instance of an application server to crash when given a particular bad input. A service that system is dependent on that slows down becomes unresponsive or starts returning corrupted response. Cascading failures, where a small fault in one component triggers the fault in another component, which in turn triggers further faults. How important is reliability? When we build large-scale systems, what can go wrong if system is not reliable? So this is the so let's take a break and make this series more interactive. So this is the question for you. Please let me know your thoughts in comment section. For now, let's move to scalability. What is scalability? Scalability is the term we use to describe system's ability to cope up with the increased load. How can we add computing resources to handle additional load? We can achieve scalability by measuring load and measuring performance. So, when we say measuring load and measuring performance, how exactly we can measure the load? What happened? If what happened if our load double down? Load can be described by few numbers, which we call load parameters. Example of load parameters can be request per second to web server, ratio of read to write in a database, and the number of active users. Once you have described the load in your system, you can investigate what happened when the load increased and system resources remain unchanged. How the performance of your system behaved, or when you increase the load parameter and keep system resources, that is CPU, memory, unchanged. How is the performance of your system? When you increase load parameter, how much do you need to increase the resource if you want to keep the performance unchanged? So now, next curiosity question comes in mind is how we can measure performance number. Usually, the describing performance, we take a help of throughput, latency, and response time. The latency, uh, what is latency? The amount of time it takes for the packet to reach the destination. Whereas the throughput is the number of records we can process per second. What usually more important is service response time. What is service response time? Service response time is the time between client sending a request and receiving a response. Now, one more quick question is latency and response time are same? They superficially are the synonymous. Let me know in the comment. Even if you make same request over and over again, you will get slightly different response. The chart over here shows the shows the response time for a sample of 100 requests to the service. Response time threshold is getting measured in percentage. Those are when we say percentage, the 95th, 99th, and 99.99 percentile are common, abbreviated as a P50, P95, P99, and P99.9. If the 95th percentile response time is 1.5 second, that means 95 out of 100 requests take less than 1.5 second, and 5 out of 100 requests take 1.5 seconds or more. Uptime is traditionally measured in nines. So remember, the more the nines, the better it is. Where exactly the percentile are getting used? Percentile are often used in SLOs and SLAs, service level objective and service level agreement. What is SLA? It is a commonly used term for service provider. This is the agreement between your service and your customer. It formally defines level of uptime of your service will deliver. Cloud providers such as Amazon, Google, Microsoft set their SLAs 99.9% and above. Let's discuss the last concept of this chapter, which is maintainability. It is well known that the majority of the cost of software is not in its initial development, but in its ongoing maintenance, fixing bugs, keeping the system operational, investigating failures, adapting it to new platforms, modifying it for new use cases, repaying technical debts, and adding new features. Yet, unfortunately, many people working on the software system dislike maintenance of so-called legacy system. Perhaps it involves fixing other people's mistake or work or system that were forced to do things that they were never intended for. Every legacy system is unpleasant in its own way, and so it is difficult to give general recommendation for dealing with them. To minimize the pain during maintenance, we can pay attention to three design principles of software system: operability, simplicity, and evaluability. What is operability? Operability makes it easy for operation teams to keep the system running smoothly. Simplicity make it easy for new engineers to understand the system by removing as much as complexity possible from the system. Evolvability make it easy for engineers to make changes to the system in the future, adapting for its unanticipated use case as requirement change. So, when we talk about operability, what can be the operation team's responsibility to keep the system running smoothly? To give a kick off to this question, I can tell you about few points. And what else you can think, please let me know in the comments. Monitoring and monitoring the health of the system and quickly restoring the system if it goes to bad state. Second point is tracking down the cause of the problem or degraded performance. With the help, how we can track those? With the help of dashboards. Maintaining the security of the system. Good operability means making routine tasks easy, allowing operation team to focus their efforts on high value activities. Second is simplicity or managing complexity. How we can manage simplicity when project get larger. Best tools we have for removing accidental complexity is abstraction. For example, high-level programming languages are abstraction that hides machine code, CPU register, and system calls. SQL is a great abstraction that hide complex on disk and in-memory data structures, concurrent requests from other clients, and inconsistencies after the crashes happen. Third point is evolvability, making changes easy. How can we manage evolvability? Make use of agile systems like test-driven development and refactoring. So, by discussing this point, we comes to the end of the first chapter. Let's recap the point we discussed until now with the help of summary. In this chapter, we have explored some fundamental ways of thinking about data-intensive application. An application has to meet various requirements in order to be useful. We talk about functional requirement and non-functional requirement. Functional requirement include how we allow data to be stored, retrieved, and searched, as well as processed. Whereas we discuss non-functional requirement such as the scalability, security, and maintainability of the system. We also discussed three main pillars to build a good system, which is reliability, scalability, and maintainability. In reliability, we discussed how faults can be in hardware and software systems and how some tolerance techniques can hide certain type of fault from the end user. In scalability, we saw multiple ways of describing load and performance quantitatively. Maintainability topic was into detail for abstraction, how good abstraction can help reduce complexity and make the system easier to modify and adapt for new use cases. That's all for folks. Thank you for watching and being patient with me. Let me know your feedback. Stay tuned for the chapter 2 where we are discussing several different data models and query language.